I welcome you all for this video lecture series on operating systems. Today our topic is allocating kernel memory. Before that, I introduce myself. I'm Shankar. I'm working as assistant professor in the Department of Computer Science and Engineering, RMD Engineering College, Chennai. Let's go to the lecture. Let's see why the kernel process, why we are allocating kernel memory space. When the process running in user mode requests additional memory, pages are allocated from the list of free page frames maintained by the kernel. Kernel memory is often allocated from a free memory pool different from the list used to satisfy ordinary user mode processes. There are two primary reasons for this. The first one is the kernel requests memory for data structures of varying sizes, some of which are less than a page in size. As a result, the kernel must use memory conservatively and attempt to minimize waste due to fragmentation. This is especially important because many operating systems do not subject kernel code or data to the paging systems. The second reason is pages allocated to the user mode processes do not necessarily have to be in contiguous physical memory. However, certain hardware devices interact directly with the physical memory without the benefit of virtual memory interface and consequently may require memory residing in physically contiguous pages. There are two strategies for managing free memory that is assigned to the kernel process. The first one is body systems. The second one is slab allocation. First, we'll see what is body systems. The body systems allocates memory from a fixed size segments consisting of physically contiguous pages. Memory is allocated from this segment using a power of 2 allocator, which satisfies the request in units sized as a power of 2. For example, 4 KB. The next one is 8 KB. 2 power 2 is 4. Then next 2 power 3, 8. 2 power 4, 16, like that. Right? The request in units not appropriately sized is round up to the next highest power of 2. For example, a request for 11 KB is satisfied with 16 KB segment because 11 KB cannot be adopted with 8, right? Because already we had discussed that the segment is using power of 2 allocator. The 2 power 0 is 1, we cannot allocate. 2 power 1 is 2, we cannot allocate. 2 power 1 is 2. 2 power 2 is 4. We cannot allocate. 2 power 3 is 8. 8 will not sufficient for 11 KB. The next one is 2 power 4. 16 KB is available. In that 16 KB, we can able to allocate only 11. The remaining 5 is free space. Right? Like that only in body system we can able to allocate. That example is given. For example, if you have a page called 256 KB, right? 256 KB. So the next we are dividing it into two halves. So what will be the next lower, because here we are dividing. So we should search for dividing the next least 2 power n, right? So the next 2 power is 128, 128. Again, we are concentrating only first left, right? So here again we are dividing into 2. The next 2 power n is 64 among 128. So 64, 64. Again we should concentrate on the left. So A, L in the sense first division is named as A, L represent left. This is A R, right side. So next divide is B, that is B left and B right. We should divide only up to the left. If the left is over, then we should move over to right. Right, again the next 64 is divided into next to lowest is 2 power n, that is 32. A next is C left and C right. Again next one is 16. After 32, 16. After 16, 8. After 8, 4. After 4, 2. So like that, the 2 power n, that possibility we should divide. Again, if the all is over, we have to come to the right parts. Like that we should trace, right? Suppose if you want to allocate 42 KB with this allocation, right? 42 KB you want to allocate with this allocation. How it will be done? Because initially we have 256, right? We have divided it into 128, 128. Again 64, 64. Again 32, 32. The least one is 32. But 32 KB will not sufficient to allocate 42 KB files. In this case, what happened? We have to allocate with this 64. So this divisions is not required. We will allocate 42 KB here and the rest will be free. Suppose after 42 KB, you want to allocate 132 KB. After 42 KB, you want to allocate 32 KB file. Then what you should do? Here in 256, we have 2 hours. First, we should concentrate left. Again, in this case, this is already allocated for 42. So here we have 64. We can divide again. It is 2 more. Here we have 132. And again, we have here another 32. This is left and this is right. In this left part, we will allocate for 32. Again, next, if you want to allocate 16, then what you should do? So again, you should come traverse, look like this. Here 128, among the 128, left is already over. So we switch over to right. In this right, again the left is also over. Again we have right. In this right as actually how many bytes is there? 32. 32 is so far, right? So again we have to divide it into 2. 16, 16. The left 16 we will allocate. The right 16 will be free. Similarly, we should do iterate or allocate the pages such a manner with this body systems, right? I hope you understood, right? The advantage of body system is how quickly adjacent bodies can be combined to form a larger segments using a technique known as coalescing. The obvious drawback to the body system is that rounding up to the next highest power of 2 is very likely to cause fragmentation within allocated segments. For example, 33 KB request can be satisfied with 64 KB segment only. That recently we had discussed. In fact, we cannot guarantee that the less than 50% of allocated unit will be wasted due to internal fragmentation. The another method is slab allocation. The next allocating kernel memory is slab allocation. Here, the slab is made up of one or more physically contiguous pages and cache consists of one or more slabs. Let's see, discuss with the diagram, then you can know clearly. There is a single cache for each unique kernel data structure. For example, a separate cache for the data structure representing a process descriptors, a separate cache for the file objects, a separate cache for semaphores, and so forth. So you just see what I said. Slab is made up of one or more physical contiguous pages. Right, where is slabs? This is one or more physical contiguous pages. See, these are all contiguous pages, right? Yes. Next, what is cache? Cache consists of one or more slabs. This is cache. This one slab. This one slab. This one slab. Right? Cache consists of one or more slabs. And kernel objects consist of objects. So this objects is allocated to the cache and cache is followed to the slabs. And this is given here. The cache will fulfill the request using a structure task structure object that has already been allocated in a slab and is marked as free. A slab may be in one of the three possible states. One is full, another one is empty, and another one is partial. Full in the sense all the objects in the slabs are marked as used. See, these objects are, all the slabs are marked as used. Empty in the sense all the objects in the slabs are marked as free. Partial in the sense the slabs consist of both used and free objects. Here actually used also is there, free is also there, right? Yes. And the next one is benefits. Benefits of this kernel memory allocation. Here, no memory is wasted due to fragmentation. Fragmentation is not an issue because each unique kernel data structure has an associated cache and each cache is made up of one or more slabs that are divided into chunks, the size of objects being represented. Memory requests can be satisfied quickly. The slab allocation scheme is thus particularly effective for managing memory when objects are frequently allocated and deallocated. As is often the case, With requests from the kernel, the act of allocating and releasing memory can be a time-consuming process. I thank you all for watching this lecture series because kernel memory allocation. Thank you.